In this section, we will be studying how to integrate expressions that involve an inverse trigonometric function. Our first objective is to be able to integrate functions where the antiderivative involves inverse trig. We have a theorem that has 3 parts and it gives us 3 separate integration formulas. Keep in mind that u does need to be a differentiable function of x and a is a positive number. So a lot of the first part of this section is going to be about pattern recognition. Example 1 closely matches the form that we have in part 1 of the theorem, because we can see we have a number minus an expression under that square root, just like we have there. So in example 1a, just matching what we see here, I'm going to take our u to be x, because I see u squared and x squared matching up there. If u is equal to x, I'll differentiate that to find that du is equal to dx. And then for the a squared, I have a squared where I have a 4, so I'm going to take a squared to equal 4, which implies that a is equal to 2. So we have our value for a and our value for u, so now we're ready to just come and fill in what this is equal to. So here we have arc sine of u divided by a, u is x, a is 2, and then we add our constant of integration c to have our final answer there. For example 1b, now I'm looking for an expression from the theorem where there is no square root in the denominator, so we're going to be looking at part 2. In this case, our u squared is matching up with 9x squared. So I'm going to let u squared equal 9x squared, which implies that u is equal to 3x, just taking the square root of both sides of that. Here I can see that a squared is corresponding to 2. Well, if a squared is equal to 2, then a is equal to the square root of 2. I'll need to finish differentiating u, because we have that u is 3x, which means that du would be 3dx. But there is no 3 in the integral. We only have a dx that we need to sub in for, so that implies that dx is equal to 1/3 du. So now I'm actually going to do the substitution since we had to solve for dx. In the integral, I'm replacing dx in the numerator with 1/3, which I'll put in front of the integral du. In the denominator, we do have a squared plus u squared. I'll just write that as the square root of 2 squared plus 3x squared. And now this form very closely matches this form. So we just need to fill out the right-hand side to get our answer. So we have 1 over a, which is going to be 1 over the square root of 2, multiplied by arctangent of u divided by a. U is 3x, and a is the square root of 2, and I'll add my constant from integration plus c. And there's our answer. In example 1c, this x on the outside here kind of gives us an indication that we will be using part 3 of the theorem, since there's this u on the outside of the square root. But to figure out exactly what u is, we're going to start on the inside, where we see this u squared minus a squared, and match that up with what we have on the inside of our square root in part c. So I can see that u squared is 4x squared, and that a squared is 9. So that tells us that u is 2x, and that a is 3. If u is 2x, that means that du is 2dx from differentiating that, and then we'll solve for dx, because we don't have just a 2 in the integral, to see that 1/2 du is equal to dx. So now let's go ahead and do our substituting. In the numerator, I'm going to replace the dx with 1/2 du. I went ahead and put the 1/2 on the outside of the integral. When we go in and start substituting here, notice that what I want in front of the square root in the denominator is u. Our u is 2x, but right now we only have an x right there. We don't have the 2. So the first thing I'm going to do is I'm going to work on rewriting this integral so that we have a u in front of that square root. So what we want in front of the square root is a 2x. So I'm going to make sure that I put a 2x in front of that. I'll put a 2 right there in front of this x, not changing anything else yet. And because I stick that 2 in the denominator, I'm also going to need to stick a 2 in the numerator. And I'm going to choose to stick that 2 in the numerator out in front of the integral. So again, I only did that so that when we actually go to do our substitution, we will pick up this u that's in front of that square root. So now let's actually start substituting. So we have a 2 on the outside of the integral. The dx in the numerator is going to be replaced with 1/2 du. That's coming from here. I'll put the 1/2 on the outside, and I'll put the du in the numerator. In the denominator, this 2x here is going to be replaced with u. And then under the square root, we just have u squared minus a squared. That's the way that we chose this. I'll just write this as using the u and a for now. The 2's cancel, so we just need to evaluate the integral, and that matches this form exactly from the way we set it up. So I know that this will equal 1 over a arcsecant of the absolute value of u divided by a plus c. And now I'll start substituting things back in. A was 3, so we have a 1/3 in front of arcsecant. Absolute value of, let's replace u was 2x, and in the denominator a was 3, and we have our constant of integration plus c.